So, this lecture is an extension of my earlier lecture, where I was discussing on the piezoresistive accelerometer design and a case study, and that is the piezoresistive accelerometer for avionics application. Two things are left, and that is temperature drift and damping. So, those two parameters are also important when we go for a piezoresistive accelerometer. Most important point is the temperature drift, because the sensing element is made based on piezoresistive sensing, and the piezoresistance is a temperature sensitive element. That many times in many lectures I have emphasized that part. And now in this lecture we will discuss little bit in detail with temperature what parameter is going to change, and because of that your output is drifting from the desired value. Okay. So, that is the major the topic of discussion in this lecture. And the second aspect is the damping analysis. How do you design the accelerometer, particularly the upper cover plate and bottom cover plate, as well as the gap between the cover plates, so that the proper damping is given to the vibrating structure, vibrating sensing element, which is the middle layer. So, there some of the definitions first let us define. One is the sensitivity is the one important aspect. So, that we will define. Before that, the output voltage, how much we get when the bridge is unbalanced. So, that I mentioned will be delta R by R into Vs, where delta R is the change of resistance and R is the no stress, zero stress resistance, and Vs is the supply voltage. So, accordingly we will get the delta V. Now, the next point is the sensitivity. Sensitivity of the bridge is defined as a relative change of output voltage per unit applied differential acceleration. So, that is the definition of the sensitivity, and it is expressed mathematically by delta V by delta G dot 1 by IB is nothing but delta R by R dot 1 by delta G. For a balanced current bridge, temperature variation changes the resistances of all piezoresistors equally, so that output of the bridge remains 0. So, that means here the with temperature the bridge resistances is going to change, but if all the resistances change equally means either positive or negative direction, whatever it is, equally all positive direction, then output voltage of the bridge should not change, because it is basically the ratio of the resistances R1 by R2 equal to R3 by R4. So, all the resistances change equally, so ratio remains same. Okay. In that case you may not get the change of the output, but the real life thing is not so. All the resistances will not change equally. So, because of that reason you will get the output voltage which is temperature dependent, output voltage of the bridge which will be temperature dependent. Now, we will see why it is not so. So, before that we have to identify what are the parameters, what are the things who can change the resistances of resistance values, and the three factors which change the piezo resistances are: one is temperature coefficient of resistance, TCR, that is because of the change of the mobility of the carrier by with temperature and with doping concentration, because you know mu, mobility of the carrier, is a function of doping concentration and temperature. Now, doping concentration, if you use a fixed value of doping concentration, then that all the resistance will have the same doping concentration, there is no change there. But temperature, again with temperature mobility will change. Now, there although the individual resistance will change because of the mobility change, but as a bridge concerned, all the bridges, all the resistance will change equally. So, in that respect, so first point, temperature coefficient of resistance is not going to change the output voltage that much. Okay. So, now coming to the second point, variation of coefficient of piezoresistivity with temperature, which is TCP, temperature coefficient of piezoresistivity, temperature coefficient of piezoresistance with temperature. Now, here temperature coefficient of piezoresistance means the resistance change because of the stress. You are applying pressure, or even if you apply acceleration, then stress is developed, and because of that the resistance is going to change. And who is the parameter? The piezoresistive coefficient, which are pi 11, pi 44, pi 12, like that. So, those pi values will change with temperature, and that change are not same for all components with temperature. If the pi 11, pi 44, pi 14 change is same with temperature, then it is not again going to create any problem, either stress is compressive or stress is tensile. The temperature variation will be not, maybe it is one negative, one positive, but with temperature the total change is same. So, as a result the bridge output may not change, but it is not fact. So, but real thing is that this change for different stress component in different, in something will increase and something will reduce in somewhere, and this increase and reduction of those values will not in the same manner in the different temperature range. So, that is the reason where the second point, second parameter, second factor is an important consideration when you go for temperature drift analysis of any of the piezo resistance. There is a third point. Third parameter is the variation of elastic constant with temperature. Elastic constants means the shear modulus or Young's modulus, those values, those constants, that are some mechanical, those are the mechanical mechanical parameters, and whether those elastic constants, that is basically coming from stress and strain, ratio of stress by strain is a modulus, Young's modulus, and the shear modulus is there. We define all those parameters. They are also temperature dependent. So, their temperature dependence is how much we will see, and because of that also the temperature, the resistance may change, and which may change the output voltage. So, these are the three parameters, and one by one we will discuss who is going to change the resistance value how much. Okay. Now, first parameter is the temperature TCR, temperature coefficient of resistance, that is due to the electron and hole mobility in silicon. Now, we know the empirical relations for the temperature as well as the doping dependence of the carrier mobility in silicon is available in the literature, the empirical relation which is noted here. Mu p, which is a function of n and T, n is the doping concentration, and what is T? T is the temperature, this temperature T in absolute scale. So, it is given by this empirical relation. So, that is why since it is empirical relation, you will see the values is not a closed form value, which is 2.35 here, 300, 0.88 here, 135. So, those parameters you may ask, how did you get it? That is, any of the empirical relation will not follow a regular pattern, a regular method by which some closed form relation you will get mathematically. Some of the parameters, numerical values you have to adjust to get the agreement with the experimental results. So, that is why those are known as empirical relations. So, for mu hole mobility or the electron mobility, similarly you can get it. The mobility with temperature and doping concentration is this expression where this n is coming here. For a fixed value of n, then you can see for temperature change the mu will change, and if mu changes, the conductivity, which is delta J by epsilon, epsilon is the field, is a q n mu n plus p mu p, where the q is a electronic charge, n and p are the doping concentration, and mu n and mu p are electron and hole mobility. So, this mu n and mu p will change accordingly, sigma will change, and sigma change means resistance will change. So, that variation if you calculate, and the plot looks like this. Here the concentration versus the conductivity, first plot, and the second plot is a depth versus the conductivity, the junction depth. As I mentioned in the last lecture, that the total resistance value is also depending to some extent the junction depth. So, here both plots are shown for different temperature. Temperature we have used 225 Kelvin to 350 Kelvin. So, the nearly over 100, more than 100 degree C variation of the conductivity with concentration, taking care of the change of mobility with temperature is shown in this curve. Now, one unique feature of this both the curves is that you can see here that the temperature variation is almost minimum for a typical doping concentration. This is this region. So, now you can see here. So, this point anyway, it's not coming. So, now you can see here this point which is here, this the temperature variation is minimum. So, here again the with high this doping higher doping concentration you can see the variation, the lower doping concentration you can see the variation with temperature, the conductivity variation, but in the middle region the almost with temperature the variation is not there. That means as well as the junction depth also is a certain junction depth, the conductivity variation with temperature is negligible. So, those plots are for different temperature. Now, that means to reduce the temperature variation, that the one parameter is the proper selection of the doping concentration and junction depth. So far the mobility variation is concerned, the change of resistance with mobility variation. We have to select the doping concentration and junction depth properly so that temperature variation of the conductivity or resistance should be as minimum as possible. So, now this is the TCR. Now, next parameter is the second parameter. We can just we will see how that also going to change, and that is the temperature coefficients of piezoresistance, that means piezoresistance coefficient effect. So, there are two major effects. One is the temperature coefficient of offset and the second is temperature coefficient of sensitivity. Temperature coefficient of offset is defined by the temperature change. This is a temperature change is a common mode effect on resistors, and so in an ideal balance bridge the offset remains 0 with temperature change. So, now the offset is coming from for what reason? So, that means the all the 4 bridges we found there are total 8 resistances, and we assume the when under no stress condition all the resistance of the 4 bridges will be the same. So, output voltage will be 0, bridge is perfectly balanced. That is in ideal condition, but in practice all the resistances will not be the same. Even it is same, you are making interconnection lines. So, those lines will induce some or will add some small value of resistances. There are contact points, they will introduce some resistance, as a result of which effective resistance of the arm, all arms may not be exactly same, and if it is not exactly same, even in the 0 stress condition you will have certain output voltage. So, that is known as offset, and that offset is not constant for different temperatures. Why? Normally if some offset is there, they should not vary with temperature, but some variation you are getting because of the change of the contact resistance and the conducting line conductivity with temperature. So, little bit variation will be there, because of that you will get the temperature coefficient of offset. That means with temperature the offset value will change, and if the offset changes, total output voltage also will change. So, at the ultimately with temperature change, the output what you are getting is a basically the combination of all effects, and they are very difficult to identify the which factor, how much change is for what factor, very difficult. But by calculation or by simulation you can know, or I can just estimate which factor is much responsible for temperature dip, who is less responsible for temperature dip. Second factor is temperature coefficient of sensitivity. This is very important. great influence because of the temperature dependence of the piezoresistive coefficient. So, that particular point we have to address much. Temperature dependence of the piezoresistive coefficient, which I just mentioned, pi 11, pi 44 and pi 14. So, now let us see the constant. Again another thing is a bridge excitation by constant voltage and constant current. So, the bridge, Wheaton's bridge which you are exciting, the supply voltage, you can excite the bridge by constant current, you can excite the bridge by constant voltage, both are possible. Now, here also it has been observed that the constant current and constant voltage excitation will not give the same performance. If we compare these two, we will find that some excitation is better than the other kind of excitation, and that has been analyzed here. You can see in this view graph that constant bridge voltage TCS, temperature coefficient of sensitivity, when V stands for constant voltage excitation, and the S is defined by pi 44 sigma L minus sigma T by 2 delta G. These are longitudinal stress and transverse stress, sigma L and sigma T. Pi 44 is a piezoresistive coefficient, and we have seen also the pi 44 is the most dominating factor among all other piezoresistive coefficients. So, this sensitivity is defined by this relation. Now, in the bottom relation, if you see, there TCS, temperature coefficient of sensitivity, when you use constant bridge voltage, that is why subscripted V, is equal to 1 by S del S by del T, that is the relation, and that is equal to 1 by pi 44 del pi 44 by del T plus, because there are two parameters pi 44 and sigma L sigma T. So, the sigma L sigma T variation is expressed by 1 by sigma L minus sigma T del pi L minus pi T by del T. So, that is temperature coefficient of sensitivity when you consider the constant bridge voltage. So, in this particular expression, both the first and second term of expression are negative. That means, the first term and second term both are negative. Both are negative means the temperature coefficient of sensitivity, if you apply the voltage excitation, is in one direction change, is adding together. But if you go for the second thing, which is constant bridge current excitation TCSI, then the temperature coefficient of sensitivity is given by this relation, which is 1 by pi 44 del pi 4 by del T, 1 by R del R by del T, 1 by sigma L minus sigma T and del sigma L minus sigma T by del T. One term has added if we go for constant current excitation. Now, here it has been observed that the first term and the third term is negative, but the second term, where 1 by R del R by del T is positive for higher doping concentration. All this positive negative I am talking, that is for high doping concentration. Since for high doping concentration, out of the three terms, middle is positive, first and second term is negative. So, overall thing will go down. So, that is why the bridge excitation by constant voltage and constant current will not be the same. So, sensitivity where we will get more, so that we can choose either, in which case we are getting much more sensitivity. Accordingly, the excitation we can decide whether we go for constant current excitation and constant voltage excitation. Now, I am coming to the temperature dependence of piezoresistive coefficients. So, if we look into that, that means the piezoresistive coefficients are although there are various parameters pi 14, pi 44 and pi 11. So, I mentioned that pi 44 is the most dominating piezoresistive coefficient. So, that is shown here. The pi value, which is function of doping concentration N and temperature T, is basically product of two parameters. One is pi naught. Pi naught is the low doped room temperature value, is a pi naught, and PNT is a function of N and T, which is a dimensionless quantity, and that parameter variation is plotted in this curve. So, pi NT is equal to pi naught pi naught into PNT, and PNT is basically a term, is a dimensionless quantity whose variation of the doping concentration and temperature was calculated by various people. One curve has been reproduced here from a paper from IEEE Transaction of Electronic Device 1982 by Kanda. So, this plot shows how the PNT varies with different temperature starting from 50 degrees to 75 degrees centigrade and different concentration 10 to the power 15 to 10 to the power 20. So, that variation, that plot shows that the pi NT at lower concentration varies much with temperature, but at higher concentration the variation is less. Now, if we calculate those values, then we get all the three parameters pi 11, pi 12, pi 44. That plot is only for pi 44 PNT variation. PNT changes here with temperature 225 Kelvin to 375 Kelvin over 100 degree Kelvin. PNTs are like that. We assume at 300 the PNT is 1, and with different if you go the higher temperature, the variation is like this. If you go lower temperature, variation is like the PNT increases, and in the higher temperature PNT reduces. Now, with that you can calculate the sigma also, that is the conductivity, and then pi 11, pi 12, pi 44. And if you look into that table, then the variation of the pi 44 over temperature is much more compared to the variation of pi 11 and pi 12 with temperature. Here is almost 7.9, 7.4, here is 6.1, 5.7, but here 166 to 110. So, that variation, the wide variation, if you take the room temperature is 138. So, now with that pi 44 variation, if you calculate, then we found that for boron doping concentration 5 into 10 to the power 18, we found that TCP is minus 2.7 into 10 to the power 3 per Kelvin, and sensitivity is 0.91427 millivolt per milliampere G. TCS is minus 2.6 10 to the power minus 3 per Kelvin. Now, for different G 1 to 13 G, you have calculated the variation of the bridge output with temperature considering PNT. So, as I told you, the variation of 3 factors, the middle one is by PNT, pi, change of pi with temperature. So, that considering that effect only, we just got the output voltage, which is 20 millivolt for 13 G at room temperature. Room temperature is here. So, you see 20 millivolt you are getting, and this is the top curve is for 13 G, and started from 1 G, this is 3 G, this is 6 G, 9 G and 13 G, and 13 G room temperature is here at the middle, and you can get is the 20 millivolt, what I showed you in earlier view graphs in last lecture, 20 millivolt. But out of the 20 millivolt, then variation below room temperature and variation above room temperature, if you look, then you find that below room temperature variation is much more compared to that of above room temperature. You see the curves, this is the room temperature value from here to 350 degree centigrade, the slope is less compared to the slope from 225 to 275 this side. So, that means the low temperature variation is much compared to the high temperature, means above room temperature. If you go for 60 degree or 50 degree temperature more, so that variation is not that much. Now, temperature dependence of elastic constants. The temperature dependence of elastic constant, if you concentrate there, what are the parameter? Elastic stiffness constants. These basically are proportionality between components of stress and strain. Ratio of stress and strain is the stiffness constant. They are designated by the term CHK, where H and K are integers between 1 and 6, like the pi 11, 12, 13, 14, 15, 16. Similarly, here also C11, 12, 13, 14, 15, 16. In that way, 6 by 6 matrix is there. So, that H and K value changes between 1 and 6. And for cubic crystal, the values are given here, C11, C12 and C44. These are the dominant terms, and with temperature the relation is given here. The variation of the elastic constant C11, 12, 44 with temperature. Now, if we calculate temperature dependence of elastic constant, then we get this result C11, C12, C1, C44 all are calculated for different temperature using that relations, and there after that the Young's modulus and the CR modulus was also calculated, and you can look here that from the values that the you can see Young's modulus 130.19. So 191 here up to this, because you see the below room temperature it is almost no change, above room temperature the elastic constant change in the third maybe second or third decimal place. So above room temperature here changes are there a little bit, but below room temperature almost constant. This is 200 Kelvin, here 300, and this is 400 Kelvin. Similarly here also variation is not that much as in your the pi, temperature coefficient of piezo resistance. Now here the variation, if you plot with temperature elastic constant variation, is shown here. The plots are taken from literature. One is by Ski Min in 1953, and another is Nikanorov et al. By 1971. That is the circle line, this one C11, C44 and C12, and dotted lines, because two literature the curves are taken from there, the elastic constant variation with temperature. Now this curve shows the bridge output voltage variation with temperature due to temperature dependence of elastic constant, piezoresistive coefficient and TCR all together, because at the end it is very difficult to find out. I told you that who is going to play how much variation. So overall variation, if you look, so that variation is plotted in this curve, and you can see here that from 225 to 325 the total output voltage variation is not small for 1G, but you can see for 1G and 3G the total variation is almost very small, negligible. But if you go for higher G, for example here is say 6G, 9G and 13G. So at higher G the temperature dependent temperature variation is much more compared to the low G variation, because their stress is less in low G, and that may be the reason where the variation is much variation is not reflected there. So now this is a P diagram. Here you can see the contribution due to different parameters. So now you can see this from the diagram. So TCR is 1.9%. Factors contributing to loss in sensitivity with temperature rise. So here the TCR variation is 1.9%. Loss due to change in elastic constant is 2%. So almost same in both the case, and rest of the 96% is loss due to piezo coefficients, pi nt or pnt. So only 2% for TCR and 2% for elastic constant. The rest of the 90% variation is responsible for change of piezoresistive coefficient, second parameter, which is much more dominant. Now here from minus 45 to 75 degrees C we have calculated, and then we found here from 25 degrees C to 75 degrees C variation is 13.4%, and from minus 40 to 25 is nearly 20%. So temperature drift at lower temperature is more than at higher temperature. So you have to take care of the situation when you are going to use this kind of sensors, the well below the room temperature, and normally for space application the temperature is well below room temperature. So there the variation will be much if the sensor is exposed to the atmosphere, but if the sensor is inside the aircraft, so their aircraft temperature is maintained not very low, is nearly 15-20 degrees centigrade. So there it will not vary much, but which is exposed to the atmosphere, that temperature is very low. So, there you have to take care of. The how to take care of. So, there are two things, something can be taken care of during your design values, means your doping concentration. I have shown you that these different the parameters, first or second or third parameter, they are dependent on doping concentration also. If you choose doping concentration certain value, that temperature variation is minimum. So, there you can adjust to some, but that may not serve the full purpose, because you can choose a doping concentration of the order of 10 to the power 19 or 3 into 10 to the power 19, something like that, but for that value maybe your temperature variation is less, but that value will not satisfy your requirement of the IC resistances where we are going to make the signal conditioning circuits. So, in that case you have to do certain compromise. So, because of that compromise, temperature variation will be there, and that can be taken care of by circuit techniques. So, you have to add certain circuits, and those circuits will take care of the variation. You have to have some lookup table inside stored in the memory of any of the processor. So, then depending on the temperature, the circuit parameter will change, and at the output after that processor, and that signal will not vary with temperature. That is the normal way of reducing the temperature variation of any sensor. Some circuit techniques are shown. Temperature drift compensation circuit. Here you can see this is the bridge, left side the R1, R2, R3, this is the total bridge, and if you connect the bridge with a circuit like that, so this will give you to some extent temperature drift compensation circuit. If temperature increases, so bridge resistance will decrease and sensitivity will reduce, but what they are doing, if we made IB, this IB which is the bias current, IB inversely, if we made IB to depend inversely on bridge resistance RB, output voltage becomes temperature insensitive. And how to make that the IB insensitive? So, that is taken care of by a circuit technique, and that is shown at the top, where this total resistance is given by RT R1 by R2, and the RT is a change which you can control externally depending on the available input data. So, these are some of the another temperature drift compensation circuit is also shown here, that they use a negative impedance converter NIC. The negative impedance converter implements a negative resistance minus Rn in series with Rb, such that Ib increase with temperature, which is Rn equal to RT R1 by R2, and that RT can be adjusted externally. So, that means resistance value is going to increase with temperature, that can be reduced by connecting a negative impedance inverter. So, that negative impedance inverter is designed with the help of a circuit which is shown here. Okay. So, there are different ways to reduce the temperature variation by circuit, and similar circuit, similar chips has come out, and some of the chips are shown here. This is the Maxim 1457 chip. The internal diagram of the chip is shown here, and basically signal conditioning piezoresistor sensor compensation circuit is available in the market, which can accurate this 0.1% accurate signal conditioner. Then here the temperature variation, all other variation due to the either piezoresistive coefficients or elastic, whatever it is, that variation is reduced to 0.1% by lot of innovative circuit techniques, and that chip is available, and people are using a chip in a multi-mode packaging sensor, and at the same time at the output they are connecting the chip, so that temperature compensation will be done. So, the specification of Maxim 1457 chip is shown here. So, this can go temperature range up to plus 125, you can see minus 42 plus 125, and its variation in different temperature range is shown, minus 42 plus 85 and 0 to plus 75, that variation of the sensor excitation current variation, supply voltage and other full scale output variation, all the things are taken care of by this chip, and this is a very popular chip as a temperature compensation or signal conditioner circuit for piezoresistive MEMS. Now, the second point is the damping analysis. So, first we have to know what is the damping and what kind of damping we are going to use in this particular sensor, and we are going to use a squeeze film damping. Squeeze film damping means a gap between your sensing element and the fixed plate at the bottom will be maintained, and because of the movement of the probe mass, the gap is going to change, and the film means air or whatever thing you allow in between the sensing element and the bottom or top plate, that is going to squeeze, and that will create a pressure in opposite direction to the probe mass. The probe mass is going to go downward, so that means some spring force will be there, and there is damping force. There are two forces working, you see, as the accelerometer vibrates. So, because of the flexure, the spring action, so there is a spring force which will be generated into the structure, and because of that some displacement will be there of the probe mass, and at the same time the damping force, that means the film which is there or the air pressure which is there in the sensing middle plate to bottom plate, that will exert some damping force, and they are trying to balance, and they are trying to come back the sensing element to the rest position. So, that is the basic damping thing. So, if you are going to define, then whenever the probe mass of the accelerometer moves perpendicular to its surface near the wall with a small signal oscillation of some frequency f, the gas in the gap will exert a back force on the mass, that is the damping. In opposite, back force on the mass, the forces have component both in phase and out of phase with the velocity of mass. The velocity in phase component is the gas damping force, and out of phase component is the spring force, because there are two forces, one is the damping force, other is the spring force. So, velocity in phase component is known as the damping force, and velocity the out of phase component is the spring force. So, those things you have to separate it out and you have to calculate. Now, the damping coefficient and damping force. The damping force is the component of the fluid force that is in phase, as I mentioned, with the velocity oscillation. It is computed by integrating over the damping area of the pressure times the cosine of the phase angle. The damping coefficient is ratio of this damping force to the amplitude of velocity of mass. The coefficient is a measure of dissipative forces of fluid. Fluid means what either gas or liquid. If you use liquid, then liquid or gas, normally gases are used with certain pressure. So, that is how much dissipative force you are going to apply on the squeeze film, that is going to be decided by the damping factor. So, these are the thing we have to select the damping factor, and that in our design specification it is 0.7 plus minus 2, we have to achieve that goal. And how do we analyze this, that is shown here. Now, the second point is the spring coefficient. Spring force is the out of phase the velocity mass, the force whose out of phase component is basically this spring force. It is the component of the fluid force that is out of phase with the velocity of oscillation. The spring coefficient again is the ratio of this spring force to the amplitude of displacement of mass. The spring force divided by the amplitude of displacement of mass is known as the spring constant. The coefficient provides a measure of restoring force resulting from the external media. So, that is the spring coefficient and damping coefficient definition. Now, how do you make the analysis? Here we have used again the coefficient where the Coventor 2000C, one MEM damping module is there, micro electromechanical system, the damping module. That module has been employed to find the value of the damping and spring coefficient for the operating environment, as well as phase angle between the force exerted by the gas on the device and the device velocity. The damping coefficient will be used to calculate the damping factor of the device. Now, these are the analysis, and it will give you much more idea of how the damping coefficient is calculated. So, in this you can, the force equation of motion is written, all of you know the equation is F equal to m x double dot plus c x dot plus k x, where c and k are the damping coefficient and spring constant respectively. M is the mass and x is the displacement. The acceleration can be determined by measuring the displacement x. Rearranging the equation here, what is shown with the second order equation of motion, the Fs, which is the force, is given by a square mx. So, x is the s square is the double derivative, you know, with respect to x, plus s cx plus k. The same equation is written in this fashion. Okay. Now, the rearranging again, the Fs by m is given by a square x plus s c by m x plus k by m x. Now, this equation, force by mass is acceleration, Fs is the force and m is the mass. So, force by mass is acceleration, it is given by a square plus twice xi omega n plus omega n square, where the omega n is given by the equation under root k by m, and this xi or z, I think this is zeta, is given by c divided twice m into omega n. This is equal to c by cc, where c is the damping coefficient and cc is the critical damping, and the critical damping is m omega n, this is c. Now, the plots are shown here. One is the damping force Newton per meter and spring force Newton per meter. The green line is the with frequency, the you can see the damping force is going to have a peak value and then it is going to reduce. Okay. And on the other hand, the spring force with frequency is linearly increases, and after some time it is going to be saturated. So, these are the two different forces that analysis has been done using the commutator wire directly. The spring force rises rapidly. You can see the spring force, which is a green color, is rapidly rises. The air captured in the cavity is squeezed, since there is no real cavity at low frequency. The air can escape with no problem, and force is small at high frequency. Air is held captive by its own inertia. So, that is the damping inside the structure. Now, here the damping force coefficient and the phase shift of the damping thing has been plotted. This is the force coefficient and the phase, and here also we found that the variation at the low frequency is steep and high frequency variation is not that much. And in the earlier diagram you can see there is a point where both the spring and damping force are same, is a crossover point, and we have to take that particular point at which frequency it is same, and accordingly the omega n value is decided, and you can calculate the damping factors in both the cases. The air gap in the simulation is 27 micron. Using those analysis we got it both on top and bottom of the probe mass. The enclosed ambient is air at T equal to 300 Kelvin and 0.1013 megapascal. Viscosity of the fluid is assumed to be 1.86 10 to the power minus 11 kg per micron second, and with that simulation we got the result. The omega n is 1.654 kilohertz. generalized mass is obtained as 7.259 into 10 to the minus 6 kg. Damping force coefficient C is obtained as 0.1188 Newton per meter second. Cc is calculated twice m into omega n, which is 0.1508, and damping ratio, which is important, which we need it, that value we got it with that simulation is 0.787, and desired value is 0.8. So it is very close to that, and actual value is 0.7 plus minus 0.2. So normally people set that value as 0.8, and in this simulation you can get that value 0.787, which is very close to the desired value. So in that way, how we are going to get this value, and that is basically obtained by changing the viscosity of the fluid, pressure of the fluid. Here we have used the air damping. So that air means how much the damping force will exert on the proof mass, that will be decided by the cavity in the bottom and top plate, and that is we kept is 27 micrometer, and the viscosity of the medium and the pressure inside the chamber. Chamber means the three pieces are there, top plate and bottom plate and middle plate. They are all these factors along with the structure, and the structure, the proof mass structure is a rectangular structure with flexure. Now sometimes the damping for small devices, if your total dimension is small, in that case the proof mass size will be again small. In that case, in order to achieve the proper damping value, which is close to 0.7 or 0.8, sometimes people go for the perforation of the proof mass itself. If you perforate that, then there is a open clear path from bottom to top, so that if the middle sensing element vibrates up and down, so the fluid may flow through the proof mass as well as the open spaces surrounding the proof mass. The proof mass is at the middle, open space is a flexure and others are open, and along with, if you put some holes through the proof mass, then also the damping factor will change to a great extent. And this is important so far as your speed of the device is concerned, and if you do not put the damping, obviously it may go to a resonance mode, and in that case the total performance or the device may be damaged. And not only that, if you do not provide the proper damping, settling time will be much more. So all these points will be there, and that is why this particular parameter is also critical, and you can design your structure. This basically is coming your structure as well as the medium which you are allowing into the cavity, and the properties of that medium, fluid medium. Those are the main parameters which is coming into the picture for calculation of the damping factor. So now with this, I think we got all the specifications. Number 1 is 13G acceleration. Number 2 is the modal analysis, the resonance frequencies will it should be above 100 Hertz, that we got it. Temperature analysis we did it, and then we found the variation due to different parameters and how to circumvent that problem. One is in the design, means selecting the parameters, that is doping concentration, junction depth, etc. Other which you cannot do, that can be compensated by using the circuit techniques that we have seen, and the temperature drift we have discussed, and lastly, which is another important parameter, that is the offset, how the offset can be reduced by some techniques of connecting the sensing elements over the Wheaton's bridge, and as well as by changing the flexure position along the proof mass, that can be further improved. So all the aspects I discussed, and with that you can get the complete analysis. And now the next point for realization is the making of the mask. After making the mask layers, then next step is how to fabricate it. In my next lecture, I am going to discuss on the fabrication process of realizing the complete structure and piezo resistances and the characterization of the sensing element, means how much values you are getting each resistance and how much is the offset voltage you are getting because of the mismatch of the bridge resistances, and how the offset is minimized with a certain circuit, and what are the output signal you are taking, then that signal some noise will always incorporate, how to reduce the noise at the output before going for signal conditioning. That means noise suppressor or some circuit techniques you have to use, so that after the amplification you will not get that much noise. So then actual static testing of the accelerometer and the dynamic testing, means the in a vibration table if you put the accelerometer, how the acceleration is, output voltage is going to change with acceleration, those things, that means fabrication part and characterization part of the accelerometer will be discussed in next lecture. Thank you very much. We are discussing on a case study, that was the development of MEMS accelerometer, that is piezo-resistive accelerometer, and in my last two lectures I have discussed in detail on the design aspects of the accelerometer along with the external circuits necessary for characterization the accelerometers. Today's lecture is on the development of the technology of the MEMS piezoresistive accelerometer. How the accelerometer is designed, that has been told already. Now the technology development as well as packaging and characterization, how it can be done, that will be discussed in today's lecture. Then the case study will be completed. So for designing accelerometer, the end of the design process is making the mask. Mask was not discussed in my last lecture. Today I will first initiate the discussion on the fabrication of mask, and then we will switch over to the technology development. Now for the layout of the mask, here first you have to design the resistance, piezo resistance, and so far the design is concerned is same as the design, resistor design used in integrated circuits. Already you know how in IC resistors are designed. It's, you have to know the seat resistance of the layer which will give the desired resistance value. Now if you know the seat resistance, then you have to select how many number of square are required to get that resistance. And in our design we found that our resistance value is nearly 1.5 kilo ohms, in that range. But one thing I would like to mention, that in any diffusion technique the resistance variation after fabrication is nearly 10 to 20%. In most of the ICs are designed in such a fashion that even 20% variation of the resistance values will be accepted by the designer. That means design should be robust, so that with that resistance change the performance of your circuit will not hamper much. Similarly here also we assume even 10-15% variation, the complete circuit should work. But here you will get the value is is a nearly 26 microvolt per G. So, that means it is highly 500 in z direction 500 microvolt and x and y direction only 26 microvolt per G. So, off axis sensitivity less, but we have to agree the fact that it is not as low as design value, because of various reasons of the fabrication tolerance is not exactly so, which is required, which is estimated in our design. So, accordingly off axis sensitivity is not that high value, but it is 500 is 26, at least more than one order less. Okay. So, now if you see the resolution studies of the accelerometer, then you can see here we can measure the resolution in the z direction up to 0.25. This is a 2.2, 2.25, this is 2.3. Here you can see 0.05, 0.05 G we could resolve the, because you can get the z axis accelerometer difference 1.197, 1.225 here. So, difference is there. So, that means up to 0.25 G you can resolve, but again it could be resolved in a further low, but because of the measurement facilities not available to give milli-G acceleration, that could not be measured. That is the limitation of our test facility. But here still we can find that up to 0.25 G, means 250 milli-G, it is resolving. Okay. So, anyway, so that is some of the negative and positive z axis, the resolution has been studied. So, with that actually let us conclude that what we did today in today's lecture. So, how the accelerometer, piezoresistive accelerometer is fabricated, that is discussed in detail, and the technology optimization has been done. Offset voltage circuit shows that within 5 volt the offset can be reduced up to 0.2 millivolt using external circuit, that is also possible. How to make the upper and lower cap layer from Pyrex glass, that has been discussed in detail, and accelerometer packaging, substrate bonding is shown, and the external circuits are also connected with the main sensing element, and at the end it has been characterized with the limitation of characterization facilities, and all these things shows that although it is not exactly the same as the design value, very close to the design value, we achieve the target specifications. And with this I can conclude this lecture, means case study on the fabrication of MEMS accelerometer using the piezoresistive pickup technique. Thank you very much.